All right, good day. My name is Stanley. Today, we'll be looking at intermolecular force of attraction and how they affect the physical properties of molecules. Now, first of all, what is intermolecular force of attractions? Because as a student of chemistry, you must have heard intermolecular force of attraction. Sometimes we mistake it for intramolecular force of attractions. They are not actually the same. All right, but today we'll be able to take a closer look at both forces of attractions so we can differentiate the differences. Now, before we start, let's talk a little bit about matter. What is matter? Matter we know is anything that has mass and occupied space. There are particles that make up matter. These particles that make up matter could be atoms, could be molecules, and these particles are held together by forces of attraction. So these forces of attractions are what holds the particles of an atom together. And these forces have a very crucial role which they play in determining the physical properties of molecules. Now, one of these forces of attractions that hold particles of matter together are intermolecular forces of attractions. You ask yourself, what is intermolecular force of attractions? These are forces of attraction that exist between molecules. That means between one molecule and another molecule. You have molecule A, for instance, and molecule B. There is an attraction between molecule A and molecule B. So this type of attraction is known as intermolecular force because they exist between molecules. There is another type of attraction that exists in molecules called intramolecular force of attraction. These molecules exist within a molecule. So, example of these forces that exist between molecules are covalent bonding. Covalent bonding is a type of bonding or type of attraction that exists between non-metals, basically between two non-metals. And what happens in covalent bonding is that there is a sharing of electron within the atom, within the molecule. There is a sharing of electrons, and it's found mostly in non-metallic compounds, non-metallic elements. Now, in ionic bonding exists between metals and non-metals. Remember that metals are electron donors. Metals are electron donors, while non-metals are electron acceptors. So the metals will donate electrons, while the non-metal will accept the electrons. That is what happens in ionic bonding. The metallic bonding is a type of bonding that takes place the within metals that are found within metals. Now, on the diagram on the screen there, you see intermolecular force and intramolecular force of attractions. Now, between molecule AB and another molecule AB, there is a link, an attraction there, which we call intermolecular force, usually represented with a dotted line. It's not as strong as intramolecular force of attraction, which is represented with a stroke there. So this is an example of intramolecular force of attractions. Let's look at the molecule of hydrogen chloride. There is an attraction between the chlorine molecule, between chlorine in hydrogen molecule and hydrogen in another chlorine molecule. So this intermolecular force is called intermolecular attractions, while the one that exists within hydrogen and chlorine is an intramolecular force of attractions. Now, examples of intermolecular force of attractions will have the hydrogen bonding, the dipole-dipole, the London dispersion forces, the van der Waals forces, dipole-induced, ion dipole, and ion-induced dipole. These are examples of intermolecular forces of attractions, but let's pick one of them and discuss on it. We're looking at London dispersion forces, so we call it the van der Waals forces. Now, what is London dispersion forces? These are temporary weak forces, right, that occur as a result of an uneven distribution of electrons in a molecule. Now, what it entails is that the particles that make up an atom, which are the protons, neutrons, and electrons, are found in the atom. The electrons are the mobile part of these subatomic particles. They move around the nucleus. Now, at an instant of time, these electrons can be found more on one part of the atom. And when that happens, there is a dipole that is already created because the electron density is crowded, is small on one part of the atom. The dipole is created. Because of that concentration of electron on one part of the atom, the positive charge in the atom is repelled to the other part of the atom. So this is what London dispersion force is all about. There is a concentration of electron on one part of the electrons, creating a dipole of negative charge because electrons are negatively charged. That will also repel the positive charge to the other end of the atom. You've already created a dipole, which is a positive and a negative. Now the neighboring molecule there is also induced by this dipole that is already created. The positive charge of one molecule will induce a dipole in the other molecule by attracting a negative charge to it, thereby repelling the positive charge to the other end of the atom. So this is what London dispersion force is all about. The uneven distribution of electrons as they move within the atom. Also, look at the diagram there. The main diagram there tells you the symmetric electron density. In this symmetric, there is an even distribution of electrons. In that place, the London dispersion force does not apply in this place because the electrons are evenly distributed. But the diagrams on the extreme right and left, there is an uneven or an unsymmetric distribution of electrons. Because as the electrons move, at an instant of time, they are found on one part, thereby creating a dipole. Now, the stronger the attractive force of this London dispersion force, the more temperature required to separate these particles. Now, what it's trying to say is that as the size of the atom increases, as the number of electrons in an atom or in a molecule increases, there is a stronger force of attractions there. And when there is a stronger force of attractions, it means that a larger amount of heat is required to separate the molecules of these molecules. So meaning that there will be a higher boiling point as a result of large electron density and a larger size of the atom. The diagram on the screen there, you see the halogens, the chlorine, the fluorine, the bromine, the iodine, and the astatine. As the size of the atom increases down the group, the number of electrons also increases, means that the boiling point also increases because as you go down the group, the number of electrons is on the increase, meaning that at any instant in time, this attractive force increases because of the large electron density, meaning that large amount of energy or heat will be required to separate the molecules, meaning a higher temperature or higher boiling point. Same applies to that of noble gases from helium to radon. As you go down the group, the boiling point also increases because as you go down, the size of the atom is on the increase, the size of the electron, the number of electrons also increases, meaning a stronger force of attractions, meaning that large amount of heat or energy is required to separate these molecules, which results to increase in temperature. So this is how London dispersion forces affect the boiling point of a substance. The more the electron density